Alright, so your I is equal to ZE square. Okay, so that's what you have as the inertial energy. ZE square e raised to power 4 m. Alright, over we have 8 pi no, that's 8 e naught square, a permittivity square. Then we have h square and n square, h square and n square. So this is what we call ionization energy. I said that ionization energy is energy required to remove an electron from one energy level to infinity. So we have I is equal to Z square e raised to power 4. Z is atomic number, E is electronic charge. That is 1.6 times 10 raised to power minus 19. M is the mass of electron. Then E naught, alright, is the permittivity, 8.85 times 10 raised to power minus 12. H is the Planck constant. Then N is the number of shells. Planck constant is 6.67 times 10 raised to power minus 34. So that is that. So now, what are the limitations to Bohr's postulate? The Bohr's postulate. The limitation, the first one is that its limitation is not applicable. All right, it is not applicable to a multiple electron system except hydrogen and other one electron system like helium. All right. So his experiment or postulation is only limited to one electron and not a multiple electron system. Okay, so that is that. Then another is that okay, the solution to multiple electronic system is actually gotten by Schrodinger. Alright, we call the person Edwin Schrodinger. So you must have heard of Schrodinger equation before. Alright, so but that is not for this level. So now the second is its postulate is based on assumption of finding electron at a particular region. Alright, so we will not do it with Schrodinger equation. So postulation number 2, the limitation number 2, its postulate is based on assumption. So the first we said is not applicable to a multiple electron system. That is the first. Then the second, its postulate is based on assumption of finding, the electron at a particular region. So, however, this is rather uncertainty principle. So we must have heard of Heisenberg law of uncertainty. Okay, Heisenberg law of uncertainty. His theory was an assumption. So now, what is Heisenberg law of uncertainty? It states that it is impossible. Don't forget that the second theorem or postulate says that its postulate is based on the assumption of finding an electron at a particular region. So, however, this is rather uncertainty principle. So, what is uncertainty principle? Uncertainty principle says that it is impossible to determine the position and the momentum of a particle, of an electron simultaneously. Let me come again. It states that Heisenberg law of uncertainty or uncertainty principle states that it is impossible to determine the position and the momentum of a particle simultaneously. That is what uncertainty principle states. Okay, so now there are equations you can use to solve uncertainty. So we have 5 uncertainties. There's what we call uncertainty momentum, uncertainty in position, this momentum, uncertainty in position. We have uncertainty in energy, we have uncertainty in time. Okay, that is for uncertainty in position, uncertainty in momentum, uncertainty in position, momentum position, uncertainty in energy, and uncertainty in time. So, and the equation that connects them together is change in uncertainty momentum dot uncertainty in position greater than or equal to Planck constant. So, if you are looking for the uncertainty momentum, so you have uncertainty momentum is greater than or equal to Planck constant over uncertainty in position. Alright, then you have uncertainty in position is also greater than or equal to Planck constant over uncertainty. Alright, you just a reverse process. Alright, this the first postulate. So if you are looking for uncertainty momentum according to Heisenberg law of uncertainty, we state that it is impossible to determine the position and the momentum of an object or a particle simultaneously. Use this to calculate for the uncertainty momentum. Why do you use this one to calculate for uncertainty in the position? Alright, then the last uncertainty principal equation is uncertainty in energy dot uncertainty in time is h over 2 pi. Okay, and h over 2 pi is 1.015 times 10 raised to the power something thereabout. So you can do h over 2 pi. H is the Planck constant, pi is 2 multiplied by 22/7. So you have a value for that. So if you are looking for, this one is for momentum and position. If you are looking for uncertainty in energy and time, uncertainty in energy, make this sort of formula will be greater than or equal to h over 2 pi, over the change in time taken. Okay, so h over 2 pi, you can resolve it if you are to find uncertainty in energy, and sometimes it's given as Planck constant. It depends on the constant that is given to you in the question. So this one is to determine momentum, this position, this to determine energy, uncertainty in energy. Uncertainty in energy is equal to h over 2 pi, all right, h over 2 pi, then over change in what? Uncertainty in time. Then the last Heisenberg uncertainty principle, all right, says that, so once we have made energy is of formula from this equation, let's make time of formula, uncertainty in time. So we have uncertainty in time taking is greater than or equal to Planck constant over 2 pi, then also over energy, over change in what? Energy. So you make it, this one is uncertainty in what? Time. Momentum, position, this uncertainty in what? In energy, E, energy, while this one is uncertainty in what? Uncertainty in the time taken. That is Heisenberg law of uncertainty. So we have been able to see how to calculate various things on that: radius, velocity of an electron, and all of those. Try to mass of an electron, atom and the likes and the likes. So now, lastly, okay, the next thing I want to do is what we call the spectral line. Okay, spectral line, because spectral line is very important for all your series, all right, in atomic physics. So we have P-Fond, we have the Balmer series, we have the Lyman series, okay, we have the Paskin series, okay. Now, if you are to determine the wavelength, all right, of a material, of an electron, now your general equation is 1 over lambda, all right, this spectral line of hydrogen atom, all right. So if you want to calculate your wavelength, 1 over lambda is equal to right back constant, open bracket, 1 over n1 squared minus 1 over n2 squared. Okay, so this 1 over lambda is equal to this. So your right back constant is 1.097 thereabouts. Okay, times 10 raised to the power, I think, minus 7 per meter. You can check that. This right back constant. So this is the value of the what? Of the wavelength, lambda. Okay, so if that is the case, now if you have to determine the wavelength of, let me say, Balmer series, so I will start from the first Balmer, so on the last. Okay, now we have Lyman series. Lyman series is a migration from that ends in n is equal to 1. All right, this is series. So we have Balmer series. Balmer series is a migration that ends in n is equal to 2. All right, and that their series line. All right, this first line, there is the shortest wavelength and there is the longest wavelength of Balmer series. Okay, so now why? Okay, Balmer ends in n is equal to 2. So let us look at the first line. For the first line is from n is equal to 3 to n is equal to 2. All right, then the shortest wavelength. This for the shortest wavelength. Then the first line is from n is equal to 4 to n is equal to 2. While the series limit, or what you call the longest wavelength, is from n is equal to infinity to n is equal to 2. All right, Lyman is only 1. All right, Lyman is from n is 8, ends in n is equal to 1. Balmer ends in n is equal to 2. So in Balmer series, you have the shortest wavelength, you have the first line. Shortest wavelength ends in n is equal to 2. The first line ends in what? N is equal to what? N is equal to, from n is equal to 4. Migrating from n is equal to 3 to 2. This one is from n is equal to 4 to 2. Then the series limit of the longest is from n is equal to infinity to n is equal to 2. So that is what we have. Alright, you can use that basically. Then Paskin series, I know that Lyman ends in 1, Balmer ends in 2. This is the shortest wavelength. This is the first line. While this one is the series limit. Then Paskin series. Alright, Paskin series ends in n is equal to 3. Okay, Paskin series ends in n is equal to 3. Migration that ends in n is equal to 3 gives us Paskin series. Okay, so that is that. All right, so now with this, now if you want to find wavelength, all right, let me say the shortest wavelength, the shortest wavelength of a Balmer series. I said shortest is from n is equal to 3 to n is equal to 2. So if I want to calculate for the shortest wavelength of a Balmer series, or let me say the wavelength of a Lyman series, Lyman is from n is equal to whatever that is ending in 1. So I have R, open bracket, 1 over. So what is the first shell? The first shell is 2 because this is migration. So I will do, if I'm doing for the shortest wavelength, I have 2 squared minus 1 over. So the n2 is what? Is 3 squared. Okay, so I will impute the value of 1.097 times 10 exponential. Rest of minus 7 here. Then, of course, you know what to do. I'll find the value of lambda. So I now have R, okay, 1.097 times 10 raised to the power minus 7, open bracket. 1 over 2 squared is 4, The equation is 9, right? You find the LCM and impute it, make random select a formula, and you have your answer. So that is what we call spectral line. Right? So that is how to go about, all right, some of the things there. So I've definitely touched most of the things that you are going to be needing. All right. So the integration of your E is equal to HF also can be part of it. Then your Millikan's oil drop experiment, all right, Stokes law, all right, all of those things. F is equal to 6 pi R eta E VT, all right. You should check those things out. Then the radius of an oil drop in Stokes law's experiment. Of course, you know that your force is given to a particular value. All right. So let me outline two things in that particular area. Charge, all right, in Stokes law is Q is equal to mgd over v. All right. So mgd over v. You can just write it down. Then your force, I think your F is equal to W plus del thrust. Then your radius of the oil drop is the square root of 9 eta v over 2 rho g. All right, that is the radius of the oil drop. Square root of 9 coefficient of viscosity, then terminal velocity over 2 rho g is the formula to use to calculate for the radius of the oil drop. Then the volume 2 is how to find it, right? Then and the potentials too is how to find it in the Millikan's oil drop experiment. Thermodynamic emission is actually the boiling off of electron from the surface of a metal. So we have deflection of electrons and the likes using E is equal to V over J. I've said that before. Your E is equal to potential over distance apart for calculating electric field intensity. So with that, I think you can navigate through all of the things you need to know for the test in Phys 142. All right. So that is that basically. So we see at the in the analysis of the other topics. So if there are questions, you can send them to me on WhatsApp. I'm going to attend to it, all right, basically. So thanks for watching and God bless you. All right.